My name is Dylan Angus. I'm from the Framework Enablement team at CodePlay. We primarily work on enabling SYCL-accelerated neural network and linear algebra libraries like SYCL-DNN and SYCL-BLAST to different frameworks like Onyx Runtime and different devices like the edge device I'll speak about today. Just to summarize, today I'll go through what is edge computing and why it's important, then speak about the different the edge computing case we use today, and I'll work together with the University of West Scotland. I'll then discuss the device and framework we use to enable this use case, and then I'll show the initial results and how we were able to prove the results through graph transformations and kernel tuning. So show of hands, who has heard of edge computing before? Okay, great. Show of hands who knows what edge computing is. Okay, not so great. So edge computing refers to the distributed computing paradigm that encourages data to be processed and stored as close to their source of origination as possible. This field came as the direct result of moving much of our compute resources to the cloud-based frameworks. And though this model allows us access to numerous accelerators to process and do computation remotely, they aren't always accessible and or even the best choice. So here are just some examples of different edge computing use cases. For instance, autonomous agricultural robotics, which often have numerous cameras connected to the host, all in need of processing. This is often in areas where there can be no reliable connection to the internet. Also, autonomous bridge surveying drones, where mapping and path planning are needed with low latency, and they can't afford lag between control commands. Additionally, the rapid movement and obstruction of these structures can make the connection to the external compute resource difficult. Additionally, they would benefit from a lightweight, compact, and low-powered computation device, especially when there are size and energy consumption requirements. So edge devices in particular, we can see that there could be a need for an edge device in which this piece of hardware can process. Sorry. With these examples, we can see that why there could be a need for an edge device, which is any piece of hardware that processes data as close to the origin as possible. They can be first entry point into a node. They can be the first entry point node into a wider, typically cloud-based network of processing nodes, filtering out unnecessary data and or doing initial processing before passing out onto the rest of the network. They can work as small but compact computers, leveraging onboard accelerators to tackle various robotics, computer vision, AI tasks directly on the device without needing an external connection. And the work I will speak about later will focus on the latter. So why are they important? To just summarize, edge devices can reduce latency and memory usage in the network by filtering the data at the origin before passing it on to the rest of the network. And they are especially important in areas where bandwidth and latency are restricted, network stability, privacy, and or security are unreliable. And in these situations, they can act as localized processing nodes. In our use case in particular, we work together with the University of West Scotland and have been doing continuous work to aerial scene understanding through multi-class classification. This presentation will focus on the performance metrics and the requirements of this use case, while the model selection and overall methodology will be published in a separate journal entry. So be sure to look out for that. Using a radar attached to a drone, we gather points around the scene and generate a point cloud of around 2,048 points at a frequency of 10 to 20 hertz. This point cloud will then be digested by a network model called PointNet to perform the actual classification task. And the Jetson and X edge device is used to accelerate the model through the Onyx Runtime framework. So the Jetson Xavier NX is an embedded device that has a CPU, general purpose GPU, as well as dedicated accelerators sold to the same board. It has 384 CUDA cores for general purpose acceleration, 48 tensor cores for tensor specific acceleration, 2 deep learning accelerators for dedicated neural network operators accelerating, example for convolution, pooling, Bash, norm, and tensor transformations. We were able to make use of the CUDA and tensor cores in our experiments, but we couldn't make use of the deep learning accelerators, which I can explain at the end of the talk if anybody's interested. So the framework we are working with is the Onyx Runtime framework, which uses the Open Neural Network Exchange Onyx which is an open source artificial intelligence ecosystem of technology companies and research organizations that establish open standards for representing machine learning algorithms and software tools. Onyx Runtime is just the model loading library that implements the ONNX standard for different backends, example, CUDA, CPU, and SYCL. Using Onyx Runtime, we were able to build on previous work where we implemented different neural network operators using a combination of SYCLBLAST, SYCLDNN, and Eigen's SYCL accelerated tensor library. Namely, we ported Onyx Runtime to the NVIDIA Jetson and then tuned the templated device kernels of our SYCL backend through SYCLDNN and SYCLBLAST. So the PointNet model is a neural network model capable of digesting a point cloud to perform classification, part segmentation, and semantic segmentation tasks. In this network architecture, we can see how heavily it relies on matrix multiplication-based operators to perform tasks which benefit greatly from the embedded accelerators on the embedded Jetson device. This makes it perfect to handle the point cloud generated by the radar. Additionally, the matrix multiplication-based operators it relies so heavily on are some of the kernels which exported template parameters that we can tune. So now I'll take you through the process of what I had to do to actually enable this on the Jetson device. It was fairly straightforward. I simply had to clone the open source DPC++ compiler and compile it with the ARC64 as a host target and CUDA as a device target. In the future, this could be as simple as installing the OneAPI-based toolkit from Intel and the OneAPI CUDA add-on from CodePlay. This unfortunately wasn't. I wasn't able to do this at first because DPC++ doesn't support the ARM with its exported packages. You have to build it from source. So the benchmark configurations for the statistics I gathered today were all run on the Jetson NX with the hardware specifications I spoke about before. To be in more detail, it also has 6-core NVIDIA Caramel ARM64-bit CPU, whose cores can be configured on and off, and the CPU and GPU clock speeds can be capped to reduce energy uses. This I will discuss on more a bit later. The OS version was Ubuntu 18.04, the L4T version was 32.5, the Jetpack version was 4.5.1, and the CUDA version was 10.2, and the CUDA version 8.0. All benchmarks were run for 1,000 iterations on the 15-watt mode with two CPUs enabled. I'll explain a bit more on what that means later, and unless otherwise specified. And results were compared between native CUDA backend and the Onyx Runtime SYCL backend. So the native CUDA Onyx Runtime backend and the SYCL backend targeting the NVIDIA GPU. So our initial performance was less than desired. At the top of the chart, you can see that the time taken to execute all of the operators was 90 milliseconds for the SYCL backend and about 16 milliseconds for the CUDA backend, which is about 4 times slower, which we can certainly do better. So first, let's look at where we're actually lacking performance. Immediately, we can see that the major problem areas were the binary operator, which does a broadcasted binary operation like add or mul, concat, which just concatulates multiple tensors together and transposes. Also, though our base convolutions were, without tuning, were about 10% as performant as CUDA, and then because our implementation is optimized for NHWC, and the Onyx spec requires that tensors are in NCHW format, the transpositions from NHWC to NCHW causes a lot of loss in performance. Thus as is, because our convolution takes up about 16% of our execution time compared to the 22% of the transposition time before and after the convolution, and the 33% concat and broadcasted binary op took up, execution time that the concat and broadcasted binary op took up, the kernel tuning we couldn't benefit much from kernel tuning here. Our graph needs to look more like CUDA, which this convolution takes up about 60% of the time. So how can we reduce the execution time of the non-tunable operators that the non-tunable operators take up? We can remove unnecessary transpose and redundant operators. Additionally, the convolutions that were initially used in the model were actually 1D convolutions, and hence we could convert those directly to matmos, and thus eliminated the need to convert the tensors from NCHW to NHWC and back. Finally, the binary ops were actually from a batch norm operation, which was converted to broadcast the binary ops, to broadcast the scale and add offsets, and thus those scales and offsets were static, and we tiled them offline and then used the entire tiled so that we wouldn't have to broadcast the operators anymore, and we just had a normal binary operation. So here we can see import performance after these optimizations, and this was done without actually changing any of the code. We just changed the graph, and overall there was about a 3 times speed up, and there was about 90% improvement in the concat and binary op. The matmul and binary op, which together take up the majority of the execution time, are now only about 30% slower than CUDA, with matmul taking about 41% of the execution time, which we can now for sure benefit from kernel tuning. So now I want to take a second to just speak about NVIDIA's tensor cores. Is everybody here familiar with tensor cores and what they're used for? Yep. So tensor cores are programmable dedicated matrix multiply and add accumulate units. Each tensor core provides a 4x4x4 matrix processing array, which performs 4x4 matrix multiplications. Thus, each core performs 64 floating point FMA mixed precision operations per clock. Additionally, CUDA provides a specialized matrix load, matrix multiply, and matrix accumulate, matrix and matrix store operations to enable these cores. To answer this, Intel worked on an experimental matrix extension to TPC++. This generalized interface is meant to unify different tensor hardware, namely Intel's AMX and XMX extensions, as well as NVIDIA's tensor cores. SYCL already supports a subgroup-based collective gem operation upstream. This gem operation is used by the matmul. SYCL is currently working on a Fuse Winograd implementation that uses this interface that has shown very good performance so far. Support for this joint matrix in SYCL can be enabled or disabled through an environment variable called SP enable joint matrix. So now I'll speak a bit about the kernel tuning process. SYCL and SYCL exposes various kernel parameters through templates such as band conflict avoidance, cache line size, and tile widths and heights. This allows us to evaluate the performance of the kernels across devices for different parameter configurations and to find the best results. Additionally, we extended previous work to expose the joint matrix parameters as well. On this graph, we show that performance of the different parameter configurations for differently sized matmul operations in the model. The matmul sizes go from largest on the left to the smallest on the right. Each point is a configuration that was tested for each matmul size and resulting G-flops. So higher is better. Here we can see that there are pockets of configurations that perform the best for different sizes, namely like here and here on top. You can see they're kind of organized into different pockets. Of course, at this point, we could just stop and just have different kernels for different size matmuls, but that would make the matmuls binaries unnecessarily large. Instead, we could look for configurations that could be shared across groups of sizes without sacrificing performance. In this graph, we highlighted the top performing configurations overall for each group of matmul sizes in various colors and plotted the actual performance for the matmul size. Blue if it's in the top 5% of that size, yellow if it's in the top 10 to 5%, green if it's in the top 20 to 10%, and red otherwise. Here we can see that for large, medium, small, and extra small groups, the same configurations are in the top 5% for each matmul size, and thus picking one of those configurations doesn't make a sacrifice in performance. Here we can see the results from the matmul performance tuned with the joint matrix implementation. We found that the tuned joint matrix implementation actually yielded 20% improvement above the baseline and is now roughly 86% of the performance of the CUDA implementation. Here we'll, at this point, this was done with the 15-watt and 2 CPU mode. And now I'll discuss the results we found that when we actually changed between the 10-watt and 15-watt CPU performance modes. So yeah, part of the reason that the Jetson was chosen for use case wasn't just the lightweight size and computer capability, but also the ability to adjust the energy use to the energy use of the device by adjusting the GPU, CPU, and EMC clock frequencies, as well as controlling the amount of cores being used at the time. We can reduce or raise the amount of wattage used by the device. The Jetson comes with 5 specified configurations, 10-watt and 15-watt modes with 2, 4, and 6 CPUs enabled, but you can also configure your own performance mode. We will primarily focus on the 10-watt and 15-watt mode with 2 CPUs enabled, as a result, didn't vary much across enabling and disabling CPUs. So as you can see here, though we had 86% the performance of CUDA in the 15-watt mode, we actually had 97% of the performance in the 10-watt mode. Additionally, the joint matrix SYCL backend for the 10-watt mode had a 28% improvement over the corresponding baseline and outperformed the 15-watt SYCL backend without the joint matrix. So let's take a deeper look into how the performance is actually affected for the different matmul sizes. The sizes here are shown in the format MKN, where the matmuls are multiplying M by K and K by N matrices. We found that for the SYCL backend, performs worse for small sizes, probably due to their runtime overhead. But for larger sizes, the SYCL backend actually outperformed the CUDA backend. We also found that there was a performance bug for one of the shapes where the left-hand matrix was a very small matrix. And here we can see the results for the memory usage overall. Like I said before, there wasn't much difference when you enabled or disabled CPUs, besides the fact that the 2 CPU mode was just slightly the best for all of them. And yeah, so other end we found that for either the 10-watt mode or the 15-watt mode, we're more than capable of operating at the 10 to 20 hertz execution frequently that we needed for our use case. And yeah, that's it. Yeah, so for future work, we're looking at improving performance for the operators like concat and transpose and softmax and pooling, enabling performance and CHW convolution implementations, as well as targeting the onboard ARM CPU and RISC-V core 3DPC++ native CPU compiler for SYCL, as well as targeting RISC-V and RBB accelerators via DPCPB through Compute Errata. We are also looking into enabling and investigating performance on FPGA development boards as a counter edge device. And please look up for the journal entry case I spoke about before. Yeah. Any questions?
Wow, SYCL in drones. How cool. Good. We have time for some questions. Any questions for Dylan? There's one at the back, and then we'll come to you.
Just one question on the choice of point net model. What kind of float point precision were you using? FP32 or FP16 as a starting base?
FP32 to start off, but we could look into FP16 to see if that affects performance. But to start off, we looked at FP32.
And then there was another question in the middle. Thanks.
Other than Onyx runtime, is it applicable to TensorRT? Like, is it possible to write a SYCL version of TensorRT backend?
TensorRT is a bit more difficult because of how the entire framework is set up. Because it doesn't just do model loading, it also does like graph transformations as well as I think scheduling and stuff like that. So it's an entire kind of framework within it itself. We wanted to test on TensorRT for our situation, but because of the Jetpack version and the Jetson, it wouldn't load a Onyx model that was post, I think, upset 14, and there weren't any conversions from upset 16 down to the acceptable Jetpack version. It's something we want to test in the future to see how well we compare it to it. But there are things in like TensorRT that I think different parts of SYCL is working on, stuff like the equivalent to CUDA graphs, which would be like SYCL graphs, and other stuff like kernel fusion and stuff like that. So we're hoping to look at those things and how that will affect us in the future. Thank you.
Just a quick question. Do you have any comparative plots maybe later for the amount of CPU bound or GPU bound the code was?
That's a good question. We don't currently have that, but that's something we'd also be interested in looking at later on. Thank you.
Okay, well, thank you, Dylan.